Welcome everyone to this seminar of Working Group 1 of the Cost Action on Relativistic Quantum Information. Today, it's my great pleasure to introduce Roger Colbeck, who is now in King's College London, but very recently was in York. Roger, thanks for joining us, and the floor is yours.
Okay, thank you very much, and thanks, for inviting me to give this presentation. So my title is Different Notions of Causation in Different Theories, and what I'm going to do is to think about what might happen in hypothetical alternative theories if they maybe do or do not satisfy different notions of causation. And a bit more about the motivation. It's not that we necessarily think these theories are plausible, but asking these questions is more about helping us to enhance our understanding of the different notions. Okay, so to start thinking about these different notions, I mean, there are several different notions of causation. The relativistic notion gives us a kind of light cone structure. And so I've just drawn an example here with A, B, C, and D, and I've drawn these variables, and I've drawn the light cones or the future light cones of A, B, and C. D is somewhere in the future here. And what this relativistic notion of causation is really about is describing something more like the potential for causation, right? So what we get from this light cone structure in the normal way of thinking about it is, well, C is outside, for example, the future light cone of A. So A, we would normally say, cannot be a cause of C, but the way I've drawn it here, A could be a cause of D, but is not necessarily a cause of D, right? So you're not necessarily causing everything in your future. And so this is why I call it a kind of potential for causation. So really what the light cone structure does is it actually is more interesting to think about the things not in your future light cone. And these are the things that you cannot cause. But things in your future you have the potential to cause, but doesn't necessarily mean you necessarily can do that, or you will do that. Okay, and the other way of thinking about cause, or one other way of thinking about cause, is from a causal model perspective. And in the causal model, we draw the quantities or the events we're interested in, or the random variables we're interested in, here A, B, C, and D, and we draw arrows between them that are supposed to indicate actual causation. So if there's an arrow here from A to D, that means A really is a cause of D, and similarly B really is a cause of C, and C really is a cause of D. But I've not got an arrow in this particular case from B to D, although D is in the future of B. So B could be a direct cause of D, but what this diagram says is actually there is no direct cause of B to D. All of the causation from B to D comes via this variable C. Okay, so at the moment I've just drawn a diagram. I'll try to explain a bit more what this diagram means later. But yeah, the main difference is the relativistic picture gives potentials for causation, while this causal model picture is supposed to indicate actual causation. And in this talk, I want to try to think about a way to try to disentangle these two. So I want to think about questions like, could there ever be causation outside of the future light cone, or even maybe perhaps cyclic causation? And so what if we break the light cone notion? So I see some people are putting things in the chat. Is this relevant questions or?
No, that was a problem, technical issue.
Okay.
It's okay.
So if there is a question, maybe shout out so I don't have to monitor the chat. I'm happy if anyone wants to ask a question at any time. Okay. So we could think about an alternative diagram like this, perhaps. So here, for example, A is a cause of C, but if this is our kind of space-time picture of these variables, C is not in the future light cone of A, and so in general, this should create a worry for us because in general it would allow signaling and lead to grandfather paradoxes and things like this. But in certain situations, it can be possible to break this link between causation and the future light cone without creating paradoxes. And that's something that I also want to talk about. Okay, let me not mention that. So yeah, so here are kind of the big motivating question, or one of the questions: is there a way to have superluminal causation while keeping some aspects of relativity, such as no superluminal signaling? Okay, so usually it's the signaling that leads to the paradoxes rather than the causation itself. And again, I'm not necessarily suggesting that the correct theory of the world is necessarily like this, but this can be an interesting question to think about and to help us understand current physics better. And maybe, yeah, in particular, there are some interpretations of quantum mechanics that have the property of superluminal causation without superluminal signaling, such as Bohmian mechanics. And there are some solutions of general relativity that even have things like closed time-like curves. So it might be worth trying to think about how such things can be made consistent, if indeed that is possible. Okay, so the brief outline of my talk. So I'm going to introduce the causal modeling frameworks, and I'm not going to assume familiarity with this from the audience previously, with apologies to people who are. So I hope that's okay. If you look at the people who are in the talk and you think everyone knows this, then I could skip through that. But I was assuming this is delivered to an audience that are not necessarily familiar with that. Then I'm going to discuss what Bell's theorem looks like within such a framework, how space-time notions could enter an extended version of that framework, and then consequences of thinking about no superluminal signaling and no superluminal causation as distinct principles, and what that means for information theory or information processing. Okay, so let me sort of try to give what I've called the usual causal modeling picture. So this was actually developed in the late 80s and early 90s, I think, mainly, or throughout the 90s. I've given these two references here, which are two books on the topic that were sort of written later looking back, but Pearl is certainly one of the key proponents of this approach and one of the key people who did a lot of the development of it. These approaches mainly dealt with the classical case, and there have been more recent developments that also try to extend this to allow for quantum notions of causation, which I'll also mention. Okay, so what were these guys trying to do? Well, they wanted to develop a mathematical theory of causation, and within it, one of the key things that you also want to do is distinguish correlation from causation, and more generally, we might like something like a causal discovery algorithm, as they're called, which is a way that you try to take some data and infer causation. So I think this theory was mainly developed not necessarily thinking about physics, but maybe things like it's coming from a statistical point of view. So maybe things like whether drugs work, for example, if you know what kind of statistics do you need to conclude that a drug is actually working, and you might want to test it against a placebo and things like this. So they sort of had this general problem, and it occurs in many branches of science that you have some data, but actually it's very important to know what the causal relation is between the correlate, or what the causes are of the correlations in that data, because if you understand the causation, then you can start understanding the mechanisms behind what's happening and, for example, then design new drugs to cure certain diseases, for example. So where does it start? So it starts by saying that a causal structure is a directed acyclic graph between observed nodes and unobserved nodes. And I'm going to draw the observed nodes in circles to distinguish them. So in essence, what we do is we go out and we observe some data, and the things that we observe, we typically associate with random variables. But we might posit that actually some of the correlations between random variables actually come about because of things that we can't necessarily see. There might be some underlying causation, some variables that we don't know about. These are the unobserved nodes in this case. And the basic idea is that, well, if we see correlations between two things, then either one should be the cause of the other. Could maybe not a direct cause, it could be an indirect cause, or they should have some kind of common cause. Okay, so I've just got this small example down here. So here we observe, there are four observed things, A, B, X, and Y. And in this case, there's a common cause, lambda, that we don't necessarily see, that we posit explains why, for example, X and Y might be correlated. Okay, so the observed nodes are associated with random variables, and okay, this isn't something in the original framework. In the original framework, which is what I'm mainly going to talk about, the unobserved nodes will also be associated with random variables. But if we think about a more general extension to the quantum case, the nature of the unobserved nodes will depend on the underlying theory. So in the quantum case, the underlying nodes wouldn't have to be random variables. They could be quantum states, for example. But because I'm sort of taking on, for the moment, the usual causal modeling picture, which I'm going to call the classical case, classical unobserved nodes are also associated with random variables. Okay, so far we've just got a diagram. How do we, how do we turn this into something meaningful? So I've just, said A causes X. I've drawn an arrow between A and X, but what does that actually mean in terms of what I'm going to see if I, for example, observe these variables? And the way that this diagram encodes, or what this diagram encodes, is actually given by this equation. So what we demand is that the variables, so this is the general case where we have variables x1 up to xn. These obey a kind of causal Markov condition, which basically says that this joint distribution of all the variables is the product of the distributions of each variable conditioned only on its parents. Okay, so the grandparents don't feature here, even though the grandparents are a cause of X, they're not a direct cause of X. In general, I mean, they might be parents and grandparents, in which case that doesn't happen. But in general, each variable should only be conditioned on its parents, and that's what this is kind of turning this diagram into a formal statement about what we expect from the correlations. Okay, so parents just means the things that directly point to you in this kind of diagram. So we're sort of borrowing parlance from family trees. But unlike most family trees, in this case, your parents can also be your grandparents in some cases. Okay, and then finally, the distribution over the observed variables is then obtained by marginalizing. Okay, so if there are some unobserved variables, we still have this equation, but then the observed ones we just marginalize by basically summing out the unobserved variables from the joint distribution. Okay, so that is at least the starting point of the framework. And Now, I guess it's useful to have an example just to get the idea. So this this example is the one that's relevant for the Bell causal structure. So we suppose we have two space-like separated devices, and we make independent random measurements on them, and we observe outcomes. Okay, and one party's measurement is called A and gives outcome X, and the other party's measurement is called B and gives outcome Y. Okay, and I've drawn here a little entangled particle that's actually, or that I'm imagining being measured, but from the causal modeling perspective, we can kind of forget that. We've just got space-like separated observations. We note that there is some kind of correlation between these variables, so it's not that these things just occur separately. And so this causal structure that's been on the slide for a while now is a natural way to try to describe this, or is a natural causal structure for this situation. Okay, so A is, we're thinking of it as a measurement, and we get an outcome X, so it's very natural for A to be a cause of X, likewise for B to be a cause of Y. And we see some correlations here, but because we're doing this at space-like separation, we think to ourselves, well, it wouldn't be very natural for the correlation to be, for example, because A causes Y or because B causes X. Because of the space-like separation, we think of a more natural explanation would be that there's a common cause, because the common cause could really be in the path light cone of these events. And so this is a fairly natural causal structure to come up with in this situation. Okay, and now if we apply the logic or the Markov condition, what this causal structure encodes is that the joint distribution of A, B, X, Y, and lambda takes the following form. Okay, so lambda, A and B are parentless, so we just write these, they don't have any conditioning. The parents of X are A and lambda, so this term appears, and the parents of Y are B and lambda, and so this term appears. So this is applying the causal Markov condition to this causal structure. We get this equation. And maybe it's just worth noting what we've actually assumed here. So if we just expand this same distribution using the definition of conditional probability, we get this set of terms. Okay, so any distribution on 5 variables, you can always write it as the distribution of the first times the probability of the second given the first, and then the third given the first 2, and so on. And so what the causal structure is encoding then can be encapsulated by these 4 relations. So for these 2 things to be equal, the probability of A given lambda must actually be independent of lambda. B given A lambda must actually be independent of A and lambda. Okay, so I'm just equating kind of term by term in this expression. And actually there are more independencies, which are all the other independencies are implied by these 4. Okay, and in general, there's a method to read off the other independencies directly from the graph, which is called D-separation, which I won't go into now if you're not familiar with it, but yeah, there's quite a nice way to, rather than fiddle around with all these probability distributions and see if they imply other ones, you can look at the graph to read off other conditional independencies which are implied by these. Okay, yeah, and finally, this lambda is an unobserved node, and so we get the distribution over the observed things just by marginalizing it out or summing it. Okay, well, I've put a sum here. In general, we might also have an integral if lambda is not a discrete random variable, but I'm just going to use sum for convenience, so I don't have to introduce measures over lambda and things. Okay, and so now based on this, I can state, or there's a way to state Bell's theorem. This is maybe not exactly the phrasing used by Bell, but this is one way to state his theorem, that there exist distributions over A, B, X, and Y that are realizable by making measurements on entangled particles, but that cannot be written in this way that we would like. So in other words, they're not compatible with this causal structure when lambda is a classical variable. Okay, and so we can go out and we can measure those distributions, or we can measure those quantum states, and convince ourselves that yes, those distributions really do obey the quantum predictions. And so there are correlations that occur in nature based on space-like separated measurements that don't have this, or that cannot be written in this causal structure, at least in the case where lambda is a classical random variable. Okay, so in light of this Bell's theorem, we have to make a choice. How are we going to sort of resolve this? We kind of want this notion of causation ideally, and this notion of causation is a very natural thing to come up with if you just start thinking about causation, but somehow it hasn't captured everything that we really want it to. So what do we do? So we've got some choices. The first choice that I've written here is we could add arrows to the causal structure. Okay, so these are some of the things that I suggested we maybe shouldn't have at the beginning, but we could say, okay, well, Bell's theorem maybe tells us that actually there had better be some extra arrow in the causal structure, or at least this is something we could contemplate. So the first diagram has a superluminal causation that A is actually a cause of Y. And this second diagram maybe appears to have a superluminal causation as drawn, but actually I could move lambda back in time and make this not superluminal. And this is essentially saying that when you thought you were making a random choice of the variable B, actually it was secretly correlated with this hidden variable that is being sent to your measurement outcomes. And yeah, these two things are in general undesirable. At least we'd like to avoid them if we can. So firstly, we've got causation outside the light cone in the first one, which is undesirable. And the second one, the thing that's undesirable about the second one is that it has a kind of causation without correlation. Okay, so in general, if this is my causal structure, we would expect B and X to be correlated, but if B and X, but actually in the distribution we observed, B and X are not correlated. So generically, if you write down correlations with this causal structure, B and X will be correlated, but the situation we actually have, B and X are not correlated. And so this is a kind of causation without correlation, which is sometimes thought of as a fine-tuning. And the reason it's called fine-tuning is if you think of a causal model with this arrow structure, it's only for a very special set of parameters that you can make B and X uncorrelated. Okay, and this actually, this idea was used in a paper of Wood and Speckens from 2015 that gives us an alternative causal modeling view that says that basically any classical causal model that exhibits Bell violations requires fine-tuning. Okay, so if you go through, I mean, I've only drawn two of them here, but if you go through all the possible causal structures that are reasonable with this, for these four parameters with some hidden variables, if you generate violations of a Bell inequality, they require fine-tunings. Okay, so that's an alternative kind of causal modeling take on Bell's theorem. And okay, so maybe we don't want to do that. And so the other thing you could do is you could alter the notion of causation. And in this case, we could model the unobserved nodes with quantum systems rather than random variables. So we have a new notion of causation. Okay, I haven't really done much in this diagram. I've just written a row instead of a lambda, but what I'm really meaning by that is that this is now a quantum state that's shared along this edge, along these two directed edges. And the distribution observed now comes out according to this formula instead. So instead of having random variables, I have two measurements, or POVMs here. For every value of A, there's a POVM that gives me the outcome X, and for every value of B, there's a POVM that gives me the outcome Y. And I ask that the observed distribution obeys an equation like this. So there should be some quantum state rho, some bipartite quantum state rho, and some measurements on the E measurements and some F measurements such that this holds. Okay, and in a way, this is just saying that the usual quantum picture of the Bell experiment is a quantum causal explanation. And just connecting back to what I said earlier about the interpretations of quantum mechanics. So the people who are the advocates of Bohmian mechanics, the way to understand their position is that they're someone who refuse to alter the notion of causation. So they're people that basically reject that this is a valid notion of causation. And if you reject that having shared quantum states can be thought of as a valid notion of causation, you're kind of forced into one of these slightly undesirable alternatives, or at least in my opinion, slightly undesirable alternatives. And Bohmian mechanics is one example where we do have superluminal causation. So we do have some extra arrows that do go outside the light cone. Okay, so that's just giving a quick flavor of using Bell's theorem as an example of this original framework. What else did people want to do? Well, they wanted to distinguish causation and correlation. Okay, and this is a very important thing for science in general, as I mentioned before. And basically the problem is if we're given some correlations, there are usually many different possible causal structures that could give rise to it. So for example, if we just have two variables, X and Y, if they're correlated, then at least, yeah, these three causal structures and more are possible ways that those correlations could come about. But of course, yeah, we'd like really to know, just because we see two things are correlated, we'd like to know whether one causes the other or which way around the causation goes. Otherwise, well, that's very helpful for us to do things.
Roger, sorry.
There's a question in the chat.
Yeah, exactly. There's a question in the chat. So Pablo, if you want to unmute yourself and ask the question, please go ahead, if that's fine with Roger as well.
Yeah, go ahead.
Yes, sorry. Just a naive question maybe, is whether one way to solve the Bell situation case wouldn't be to just upgrade everything, like all probabilities become quantum amplitudes, complex numbers, but then you keep the rest equal, the conditioning, well, yeah, the separability conditions equal.
So you want to change the notion of probabilities. So
yeah, because in the end you're changing the resources, but not the probabilities. Why not just change everything?
So I think well, yeah, okay. I've not thought too much about this approach, but I think we don't necessarily want to think about the things we observe not using the random variable picture. Perhaps there is a good argument why we should do that, but using random variables for the things we observe seems to be a very natural thing. yeah, I'm not sure exactly what the alternative you're imagining is, but of course we could have probability distributions with complex numbers in them or something, but then we still need to turn this into a real number to actually get a probability, because what does it mean for the probability to be half plus half I or something? So I think because the way I understand probability theory, I do want probabilities to be positive real numbers between 0 and 1 that sum to 1. I don't want to allow other things in there because, well, I could allow other things there, but then I need an interpretation of what it means if the probability is a complex number, for example. So I'm not sure if I maybe I didn't quite understand what you're getting at.
No, that's fine. I mean, I believe there is some kind of operationalist premise of, actually observing probabilities in what you suggest. Yes.
Yeah, indeed. So this is coming from a very operational point of view where I imagine myself as an agent. I see things and I use probability theory to model my observations. Now you could say that's a bit agent-centric and not maybe very kind of right for a fundamental theory, but I think as the way I interact with the world, I think this is a very good way to model things.
I was just suggesting, I was just wondering whether people have considered trying to build causal models of why should this particle be in this superposition of amplitudes? What are the causes of it? So just, fully quantum, but okay, fully coherent. But okay, that was my question. But
Okay, yeah, I'm not sure about those approaches. So.
Right.
Okay, yes. So I was just saying, yeah, there can be different causal structures that have the same, that gives rise to the same correlations, and we want to try and distinguish or try to say which way round the causation goes. And one way to do this, or the way the standard causal modeling framework of Pearl et al. Tries to do this, is to use the concept of an intervention. And what an intervention is supposed to correspond to is taking an action that may disrupt the causal structure. So maybe it's helpful to have a concrete example. So I could imagine maybe that these two random variables, x and y, perhaps x is like the front of my house is wet, and y is that the back of my house is wet. And of course, I noticed that these are quite highly correlated, namely that when it rains, it tends to be that both the front and the house and back of my house are wet. So this seems to have a reasonable common cause explanation intuitively. How could I actually sort of distinguish that by intervention? Well, what an intervention corresponds to doing is kind of forcing one outcome, even though it wouldn't be happening naturally. So what I could do is wait for a sunny day. If I wait for a sunny day and I spray the front of my house with water, and then I go and check around the back, it doesn't make the back of my house wet. Okay, so it seems from that intervention, I can start to build evidence that front of my house being wet is not the cause of the back of my house being wet. Okay, and vice versa. And so this helps us to sort of lead towards the common cause explanation. But I said use intervention, I put in brackets, if possible. So in some cases, you may not be able to do the intervention you'd like to, either because it's unethical or because it would just be sort of too expensive. So in some medical trials, or maybe if you want to decide whether taking a drug has a particular side effect, it's maybe what you'd like to do is take people without the disease and give them the drug to see if they get the side effect. Now, you can't, it's a bit unethical to just force random people to take a drug that they don't need just to test this theory. Okay, maybe you can make it more ethical by asking their permission and so on. But in some cases, you can't do or it will be very unethical to do the tests that you might want to do. Or in other cases, maybe it's just too expensive or too difficult. So we believe that the moon causes tides, and a nice way to test that might be to remove the moon. But of course, that would be quite difficult. So we wouldn't be able to actually do that intervention, and so we sort of infer that might happen by some other observations. Okay, so what intervening corresponds to doing mathematically is kind of cutting arrows to the variable being intervened on. So if we intervene on x, what we basically do is we cut any incoming arrows into x, and we're basically forcing x to take a particular value. So when I spray the front of my house with water, I'm forcing the variable x to have the wet state, even if it would otherwise be dry, according to what else is going on. And this so we have our initial causal structure G, which could be one of these three things. And once we do this intervention, we form a new causal structure G do X. This is the thing we're intervening on. And that causal structure is basically formed by cutting the incoming arrows to the variable X. Okay, and now we're going to say that X affects Y if for some choice of X, these distributions written here are not the same. Okay, and so if for some value of X, when I intervene and force X to be X, this gives me a different distribution on Y than when I don't. Okay, and this implies if X affects Y, this implies that X must be a cause of Y as well. Okay, but the converse doesn't hold, so it can be the case that X is a cause of Y without X affects Y, and this is actually an example of the fine-tuning that I mentioned before. Okay, so this is how the approach tries to distinguish causation from, or how it tries to get from correlation to causation, to understanding which causal structure is really at play. By using these interventions, we can tell whether X causes Y or the other way around, or whether they maybe have a common cause.
I have a quick question, if I may. So in the previous case, if you have a cyclic causal structure, so X impacts Y and then Y also impacts X. So then if you do the do, then you remove the arrow from Y to X. But then this equation will not be true, but still X would impact Y. No.
Yeah, so at the moment I'm not having cycles in my causal structures, right? So this is all for the case of directed acyclic graphs.
Right.
Yeah, we have thought about the case of cycles, and yeah, this is in another paper that I have with Villasini, or I think it's one of the ones that I referenced on the front. But yeah, I don't want to get into this. This does make things more complicated. I don't want to get into that in today's talk. But yeah, happy to discuss it sometime. Yeah, so here I'm talking about the fairly standard model of causation, where we start with a directed acyclic graph. Yeah, okay, so this is this intervention concept, and yeah, maybe to say a little bit more how we actually use this. So although we may not know them, we imagine that there are underlying mechanisms behind the observed correlations. So here's a slightly different or slightly simpler, or here's a causal graph with X and Y. Here there is a common cause of X and Y, but X is also a direct cause of Y. And in order to really specify the distribution in this situation, what I have to do is specify mechanisms. So how does X relate to lambda, and how does Y relate to X and lambda? And so when I write down these conditional probability distributions, this is my way of specifying the mechanisms by which these correlations are produced. And these may be deterministic, and if they're deterministic, then there are just simple functional relations, like x is a function of lambda or y is a function of x and lambda. But in general, they could be probabilistic. And these same mechanisms are assumed to hold under the intervention, except for the node or nodes that are being intervened on. Okay, so what I kind of mean by that is if I do an intervention on x, or as a specific example, if I do an intervention on x, the distribution over y will still come out according to this same mechanism here. Whereas if I do a distribution on x, I don't get the same p of x. X is now just fixed to whatever I make my intervention. Okay, so this sort of helps us to infer what, or to think about what the distribution will be in the do causal, the do version of the causal structure. And this intervention is operational. We imagine it can in principle be done, even if it may be technically or ethically impossible. And in some cases, the post-intervention distributions can be inferred directly from the original distribution without further experiment. But in other cases, and there's a set of do calculus relations. Again, this goes back to Pearl, that relate features of the distribution in the do graph to that of the original distribution. Okay, these won't be too important for the rest of the talk, but I just mentioned those. Okay, so now we can maybe move to, that kind of covers the framework part of the talk. And now I want to think about, or that's the original framework part of the talk. And now I want to think about how we can also introduce concepts of space-time into the picture. So causal models encode properties of probability distributions, but to include space-time, we need to upgrade the random variables that we were talking about before to ordered random variables, where we want to associate them with elements of a partially ordered set. And for the purposes of this talk, just think about Minkowski space-time as my partially ordered set, because we don't need to get more complicated for today. One second, I just get a quick sip of water. Sorry, my throat has gone very dry. I think I'm talking too much. Okay, so yeah, so we take what was a random variable x before, and we form a new thing, which is well, I've called it here this calligraphic x, and we just take the original random variable and we give it a location in space-time, this bold x. Okay, so yeah, so now I'm sort of moving to a new framework that with Villasini we came up with in this paper. So each random variable now just gets a space-time location, or in general a position in a partially ordered set. But yeah, let's think about space-time for this talk. And we're just going to call this an embedding of the causal model into space-time. Okay, and now we want to think about whether our embedding has certain compatibility notions, and the first one is no superluminal causation. So if I have a causal model and I have a particular embedding, the embedded model satisfies no superluminal causation if whenever the causal structure has an arrow from x to y, then y is in the future of x in the embedding. Okay, so to say it more simply, causal arrows only point to the space-time future. Okay, so that one's fairly straightforward. And then no superluminal signaling. So I'm just going to give a simplified version of it here. The full version is a little bit more complicated, but the technicalities aren't really needed for today. So this is based on the set of effects relations, and the set of effects relations of the embedded causal model should have the property that, for instance, if x affects y, then f of y, which means the future light cone of y, is contained in f of x, the future light cone of x. Okay, and similarly, x affects two variables, y, z, requires that the intersection of the future light cones of y and z should be contained in the future light cone of x. Okay, and what this basically tries to say, or to say it in a simple way, is basically that you can't use interventions to send signals outside the future light cone. Okay, so it's supposed to capture quite a natural property. And furthermore, just a remark about the one connection between the two, because x affects y implies x is a cause of y, no superluminal causation implies no superluminal signaling. So these principles are kind of ordered. Okay, so maybe it's helpful to have an example of when these two things can be different, and want to think of jamming, so-called jamming, as this example. So here's a causal structure for jamming. There are three observed things, B, X, and Z, and possibly some unobserved variable as well. And the correlations, I mean, basically you can think about X and Z, or all of these three things are bits. And the case of jamming, X and Z are uniformly distributed bits. And essentially B gets to decide whether X and Z are correlated or anti-correlated, or whether X equals Z or X does not equal to Z. Okay, and so the correlation satisfy B is the XOR of X and Z. So if B is 0, X and Z are the same. And if B is 1, X and Z are different, and X will always be uniformly distributed. So a kind of way this can arise is if you have lambda as a uniformly distributed variable, you take x equal to lambda and z to be the XOR of b and lambda, then you realize these jamming correlations. Okay, so this is all fine. And by the way, this was kind of thought about in this paper, but when it gets interesting now is when I start to put things into space-time picture. Sorry. And if I try to put these into space-time as shown in this diagram, then we get something that doesn't fit with our usual causal modeling. So what are the effects relations? Well, here B affects XZ jointly. Okay, so if you have access to X and Z, you can infer something about the distribution or about the value of B. But if you only have X, actually you can't tell anything about B, and if you only have Z, you can't tell anything about B. Okay, and so that means that with this light cone structure as drawn here, we can actually have no superluminal signaling. Okay, and the reason we have no superluminal signaling is that, so B is the kind of input here, or we're imagining intervening on B and trying to send a signal to agents who have either access to X or Z. Well, because B, the distribution or changing the value of B has no effect on the distribution of X individually and no effect on the distribution of Z individually, the only way we can receive a signal from B is if we have both X and Z together. But because of this space-time arrangement, that will only be in the intersection of the future light cones of X and Z, and that's already in the future of B. Okay, I didn't even draw the intersection because my light cones don't go far enough, but it's up here where my cursor is here. Okay, and this actually motivates this this is why we have this intersection of light cones in the definition here. Okay, and so the result of all this is just that with this embedding, I mean, we do have superluminal causation. If you look at the causal diagram, we need B to point to X, and that does go outside the light cone if you think about an arrow going across here, but there is no superluminal signaling, and this is what this paper tried to think about. Okay, so that just tries to illustrate those two different conditions. Okay, so I've got about 10 minutes left, I think. So I'll just try to explain a bit now about the differences between these two principles for information processing. And what we're going to do is consider the task that, or something that we talked about earlier, which is the task of generating correlations that violate a Bell inequality. Okay, and this is a precursor for other things. So device-independent quantum key distribution, for example, requires Bell inequality violations. So there are lots of information-theoretic protocols that that rely on this. Okay, so what this means, and now I've, instead of X, Y, A, and B, I've just changed to X, Z, A, and C. But this is essentially an equation that we had before. Okay, I've written it with the conditioning now, but we want to find a distribution P, X, Z given A, C that cannot be written like this. And we want to do it in, and we're going to consider two space-time embeddings in order to do so. One is this one, space-time embedding A, which corresponds essentially to the one we used before with the when we were talking about Bell's theorem, except with the relabeling of variables C and Z instead of B and Y. Okay, and the second one here is slightly different because now X is no longer in the future of A and Z is no longer in the future of C. Okay, and the task is then within using these space-time embeddings, can we generate correlations that cannot be written in this form? Okay, and now the first two results are those with no superluminal causation. So all these results are, the references. Okay, the reference is coming up later. Sorry, I think I should have put it on the slide, but I didn't. Yeah, it will appear later. So the two results with no superluminal causation. The first one is that Bell inequality violations, by which I mean producing correlations that don't obey this relation, cannot be realized in any classical theory satisfying no superluminal causation in embedding A. Okay, this perhaps shouldn't be so surprising given Bell's theorem. We can think of this as a restatement of Bell's theorem, but working it through with this causal picture. Okay, and the word classical is important in number one because we know that we can get Bell violations with this space-time picture if we have shared quantum states. So in a quantum theory, we can violate Bell inequality. We can get Bell inequality violations with this space-time embedding. Okay, and secondly, Bell inequality violations cannot be realized in any theory, classical or otherwise, that satisfies no superluminal causation in the second embedding. And okay, roughly speaking, the idea is that, well, if we don't have superluminal causation, then we also can't have superluminal signaling. And that means that A and C must be uncorrelated with X and Z. And so we can't have any interesting correlations. So P of XZ given AC will just be the same as P of XZ. And any distribution P of XZ can be written in the form required here. Okay, and now a slightly more interesting case. What happens if we drop no superluminal causation, but keep no superluminal signaling? Okay, so this is kind of the whole point of doing this. We usually try to keep no superluminal signaling because we're worried that superluminal signaling is the thing that leads to paradoxes. But we're sort of trying to probe what might happen if we do allow superluminal causation. Okay, and in that case, Bell inequality violations can be realized in any, even classical theory with jamming, satisfying no superluminal signaling, using either embedding A or B. Okay, so if we embed the variables either according to embedding A or even according to embedding B, it is possible to have violations without violating superluminal signaling. But we do have to violate no super causation. Okay, and so to briefly explain how that works, what we're going to do is introduce a new variable B and allow this to have the jamming correlations with X and Z. Okay, so I put this variable B at this location in this embedding and at this location in this other embedding, and the point is that B is both in the future of A and the future of C, but that the intersection of the futures of X and Z is contained in the future of B, which means we can do the jamming without superluminal signaling. Okay, so that's kind of the reason for choosing these regions like this. Okay, so how does it work? So we're going to have B that does the jamming of X and Z. And what's going to happen is basically A and C, these are just observed random variables, they're going to get sent to B. Okay, and we're going to take B to be the product of A and C. So again, everything is binary variables, either zeros or ones. Okay, now because B is jamming with respect to X and Z, the XOR of X and Z is the same as B, which is this product of A and C. And for those who are familiar with non-locality, will recognize that X plus Z equals A dot C is exactly the requirement of a PR box. And for those who aren't familiar with it, the PR box is something that achieves the maximal possible violation of this Bell inequality, of a Bell inequality. So it's essentially the most, I mean, I just write cannot be written like this, but it's essentially the thing that's furthest away from a distribution that can be written like this in a certain sense. Okay. So we should just check that this does satisfy no superluminal signaling. So because B is in the future of A and C, the effects relation that A affects B and that C affects B doesn't mean that there's superluminal signaling. This is not a problem because if A affects B, then we just require that B is in the future of A to avoid signaling, and B is in the future of A, and similarly C. Okay, the intersection of the light cones of X and Z is contained in the light cone of B. So B affects XZ also does not lead to superluminal signaling. So this is the jamming property. The fact that it's jointly affects these two, but not individually, makes this not signal. And again, yeah, because of jamming, B does not affect X and B does not affect Z individually. So X and Z can be outside the future of B while still respecting no superluminal signaling. Okay, so this is a way to distinguish no superluminal, or to, I mean, in principle, if this was the theory, we would be able to certify that we have no superluminal causation without violating no superluminal signaling. And yeah, just an interesting remark that the possible positions of the variables depends on the number of dimensions. So in 1+1 dimension, so one spatial dimension and time, the intersection of two light cones is itself a light cone. And actually that means that we can move B anywhere we want within this kind of indicated region in this embedding, or anywhere in this region in this embedding. But interestingly, if we go to higher dimensions, so in 3+1 dimensions, in the kind of frame shown, B has to have an earlier time coordinate than X and Z. So it must be earlier in time than this line here. I mean, in this frame, X and Z are simultaneous in order for this light cone property to hold. So if we moved B in above this orange line, actually the future light cone of B would not, the intersection of the future light cones of X and Z would not be contained within the future light cone of B, even though it looks like it from this this diagram, but this diagram is only for 1+1 dimension. Okay, and similarly in this case. So this is a kind of interesting thing that these locations actually depend on the number of spatial dimensions. And yeah, furthermore, in 1+1 dimension, we can also move X and Z as far back in time, or as far back along their past light cones down these arrows as we want, and still have this no superluminal signaling property. But again, in more dimensions, this doesn't hold, and we need to make sure that B remains in the past of X and Z in this frame. So that's just an interesting remark that the dimensionality actually plays a role. And yeah, given the causal structure, this is somewhat counterintuitive, because if X and Z can then go arbitrarily into the past with respect to this variable B, but the causal structure says B should be a cause of X and Z. So this is sort of not only superluminal causation, but it's causation arbitrarily far back in time. But in 3+1 dimensions, we can't push these arbitrarily far back. So perhaps this can be thought of as a reason why we have at least more than one dimension, of one spatial dimension. Okay, yeah, I won't take up too much more time. There's just a couple of small things to say. Sorry, I think I might have basically hit the hour now. So yeah, this jamming and PR boxes are two hypothetical types of system, and they're usually introduced not as things that we think are necessarily going to exist, but as ways to understand properties of quantum theory. So there's been a lot of work trying to understand the question of why nature allows Bell non-locality, but for example, does not allow PR boxes, even though those you know, they're also non-local things. They don't allow signaling. Why should nature have decided to limit itself to quantum theory and not gone all the way to PR boxes? And yeah, there's a whole slew of results, some of which I briefly list here, that basically come up with things that are strange if our world had PR boxes. But because jamming can be used to create PR boxes, as we basically saw in this protocol, many of these implausible consequences will then also carry over to jamming theories. So instead of introducing PR boxes as this new hypothetical type of system, we can also think about what would the universe or what would the world be like if these jamming systems exist. We still wouldn't necessarily be able to signal, but what could we do instead? Or why did the world not decide to allow us jamming? You could ask it that way, and several of these things for PR boxes would also carry over. And yeah, one final sort of interesting remark on this. So by using jamming, we can generate PR box correlations between two parties in half the light travel time between the parties. So if we imagined a theory where there were PR boxes, we might expect, so these blue things are supposed to be halves of PR boxes. We might expect that, say, Alice could make a PR box here and send one half to Charlie, and then Alice and Charlie would be able to generate PR box correlations. But this will take the light travel time from Alice to Charlie. Now, if Alice and Charlie originally share jamming correlations, these jamming boxes are shown in green here, then then actually the light travel time to achieve PR box correlations can be halved. And what has to happen is, just like this protocol, Alice and Charlie send their inputs to a third party in the middle who takes their product and inputs it into this jamming box, and then out come X and Z. And now in only half the light travel time, we've generated the PR box correlations. So this is maybe just to say that jamming and PR boxes aren't completely equivalent to each other, but yeah, they have this interesting connection. Okay, so I think that kind of completes what I wanted to say. Yeah, these last results that I mentioned are all in this archive paper. Sorry, that reference should have appeared earlier as well. So yeah, what have I done today? I've explained the causal modeling approach. I've introduced parts of, or I've explained the usual causal modeling approach from Pearl. Then I've introduced parts of our new framework that extends this to allow for quantum causation, fine-tuning it, and it does extend to cycles as well and other things that I didn't talk about today. I've discussed the principles of no superluminal causation and no superluminal signaling in this framework. So I've shown that these principles, how to formulate these principles within this framework, and this is kind of a first case study showing that there are theories in which that could in principle operationally distinguish between these two principles. So we can find theories that don't allow superluminal signaling but necessarily do have superluminal causation, which we showed by considering this information processing task. Okay, so slightly overrun for time, but I'm happy to take questions if anybody has any.
Thank you, Roger. Thank you very much. Destiny, would you like to lead the discussion?
Yes, sure. Thanks a lot, Roger, for the interesting talk. Do we have any questions in the audience?
I have a question if I can ask.
Yeah, go ahead.
So I guess this particular jamming scenario that you describe that leads to the PR boxes has to do with also the dimension of the random variable, because there are two in this case. Suppose I want to have a similar scenario where these random variables have different sizes in general. Yes, right. So would it be fair to say that then I should be looking for trying to construct a correlation such that when you marginalize on one of them, then you get a maximally mixed correlation on the other variables?
So you're trying to think of an extension of this jamming box to random variables with more outcomes.
Yes.
So the key property that you want is that there's no correlation between B. Go back a bit to where I started with jamming. Yeah, do you want that there's no correlation between B and X for any value of B? So you want X to be uniformly, or have in general the same distribution independently of B, and similarly Z. So the natural extension would be to make this addition modulo the number of possible outcomes of these random variables. So if I want these random variables, instead of being binary, to have 10 outcomes, then I just add modulo 10 here, and I make these uniformly distributed from 0 to 9, and these uniformly distributed from 0 to 9.
Yeah, I'm just wondering if this is the only way of doing this. So I understand that if you do this, then this property would hold, like, because of the PR boxes, a natural extension of that when you go to more number of output sizes. So there exists like some non-local boxes when you marginalize that you don't get the maximally mixed on one of the subsystems. So if I want to work back to the jamming scenario, and I want these kinds of correlations, would adding them be like the only way to generate them, or could there be some other Boolean function, not Boolean in this case, but functions that can also realize this?
I mean, the key thing, I mean, this property that B does not affect X, this is quite a special property. This essentially means, in a way, you have to use lambda a bit like a one-time pad to hide any information about B in X. So I've sent B over to one party, and I want to make sure that X contains no information about B. And then there's this kind of Shannon result that in order to do that, I should basically this needs to be as long as B, needs to have as many, the cipher, the key needs to be as long as the message, and then I should just add them together modulo the message size. So I'm not sure there's going to be other ways to do it, but I haven't considered it too deeply. That's just the first thought off the top of my head.
Yeah, it makes sense why adding them would be a natural extension. Yeah.
Thanks. Do we have any other questions? But maybe I can ask a question. So I was curious about your thoughts on, so there's this gap in information processing between these two sort of theories. And of course, it's, as you showed, it's related to the task of generating non-classical correlations. What might you speculate about, say, the possibility of some cryptography task or randomness, or one of these sort of other, what one might say, so-called practical tasks that rely on generating Bell violations?
Yeah, I mean, I guess this
It's a bit more
is,
speculative, I guess, but
well, this is some, where is it? Where did I mention? Maybe when I introduced this, yeah. So this is a precursor for something like device-independent quantum key distribution. So if you can, so in a way, yeah, this is a sort of cheat to avoid going into all the details. I sort of want to make the logic that if we can generate correlations that violate a Bell inequality, we could do device-independent quantum key distribution. That's sort of already known. And so by showing that we can generate correlations that violate a Bell inequality, in principle, we could use those for device-independent quantum key distribution. One has to be a little bit careful about that because of the causal structures that we're imagining. So yeah, I guess if we have a theory with jamming, we ought to also think about an eavesdropper who has access to jamming systems, and whether the proof that device-independent quantum key distribution is possible, for example, still holds in the presence of an eavesdropper with jamming correlations. So it is known that you can do device-independent QKD in the presence of an eavesdropper with access to PR boxes, although you can't using the usual quantum protocols. So this is an interesting, an interesting thing. So you have, but there's a paper of Barrett, Hardy, and Kent from about 2005 that showed that it is possible to do device-independent quantum key distribution against an adversary who has access to PR boxes. That analysis, as far as I know, hasn't been done for an adversary with access to jamming boxes. Just trying to see what my intuition tells me about whether it should be possible or not. But yeah, I think in the same way, it's probably won't be possible to use one of the usual protocols, essentially for the reason that the jamming correlations can be used to make PR boxes, and we know that PR boxes can't be used, or theories with PR boxes don't allow the usual device-independent quantum key distribution protocols to be used. Yeah, maybe I'll stay on the fence as to whether a modified protocol might nevertheless enable that. But it seems I wouldn't be surprised if it was possible.
That would be interesting indeed. I guess maybe it's also related to the question of with PR boxes, you can formulate them as a GPT, like a generalized probabilistic theory, but probably this is not so clear for the jamming case, because here it's not just dependent on the probabilities, but also depends on this particular space-time configuration where you have this kind of intersection.
Yes, indeed. I mean, jamming boxes are very weird. So what you actually, to properly think about these in a theory, I think you also have to say what happens to them when they're used in different space-time configurations. So the way I mean, I didn't really go into this in detail today, but the way I've kind of put them in this diagram, I'm sort of imagining the space-time configuration is like this, and when the space-time configuration is like this, we really get the property that whatever you input here is the XOR of X and Z. But now if I move this middle box and keep these two the same, in the same position, if I move this middle box, say, yeah, I mean, somewhere, say, into the plane as it's drawn here, if I go far enough, there will be signaling. Now, if I just realize naively the jamming correlations, depending on the position of this box, it will enable signaling. And so actually to embed this in a proper theory and respect no superluminal signaling, these boxes have to change behavior depending on their relative space-time locations. So I think this is in principle possible to imagine and still maintaining no superluminal signaling. But yeah, indeed, the theory would have to account for that behavior and take that into account when trying to answer the question of whether you could say do device-independent quantum key distribution or not.
Yeah, thanks. That would be interesting question to look into, definitely. I think, and probably depends also on the space-time dimension. So since the list of possible locations where this can still work without superluminal signaling really depends on the dimension. So
yes, indeed. So I think in general, basically 1 + 1 dimension is special. That's my intuition. And then once you have more than one spatial dimension, I think you roughly get all the same phenomena. But I guess the case of 3 + 1 is the most interesting one to care about.
Yeah, thank you. Do we have any other questions? Last moment questions? Okay, if not, let's thank Roger again. Thanks a lot for your time and the talk.
Yeah, no problem. Thanks for inviting me.